Okay, this is the third one on the revision section of solutions. Again, I'm going to go through the probability problems. There's a couple of questions in here which might be new to a few of you if you didn't do any of the extended work. So hopefully this will take about 25 minutes. Opening with some fairly straightforward questions, but notice the star indicates that I should show some good working. So there are only black balls and white balls in the bag. A and B is shown in the diagram. Heidi going to take the random ball from bag A, and the random ball from bag B. Which bag gives her a better chance of taking the black ball? So what we need is the probability A black. What goes in the brackets just has to describe the situation. It doesn't matter exactly how you do it. And that is 1, 2, 3 out of 7 are black. That's the probability of getting a black ball. Let's look at B being black. Again, how many black balls? 1, 2, 3, 4, 5. How many balls altogether? 5, 6, 7, 8, 9, 10, 11, 12. And the question is, which one has the greater? You could cross multiply to get the same denominator. So let's cross multiply. I could do multiply that one by 12, multiply that one by 7. And that would be 36 over 84. And this one would be 35 over 84, which would show that A is best. And state it. Just showing the numbers doesn't work. You could also compare them by decimals. So you could do 3 over 7. And that's 0.429. And 5/12. Which is 0.416 recurring. And if you compare those, this probability is greater. So the probability of A is greater than the probability of B. There's a greater chance. Question 2. Listing all possible outcomes. It's best to work through things in a logical manner with this. So if I do Dodie on the first line, who can he be paired with? Because it's one of that from each. So for each boy, we need each girl. So we could have Anna. Dodie could also be paired with Michelle, James, and Anna. And once you get to somewhere about this, you've probably got the first point because you've started showing all possibilities. James and Michelle. So these are the people she chooses, it's not the teams. Okay. I was just checking, because if it was the possible teams, then the chances are you might need to say Jeanette plus. So it's worth checking the reading. Write down the possible combinations Jeanette can choose. So these are her choices on the basis that she's going to be playing as well. So the next question is, there are only red counters and blue counters in the bag. The ratio, the number of the counters in the bag is 4 to 6. I think we've seen this in a ratio question in the previous video. Write the set ratio in the simplest form. So both of these will share by 2. So we get 2 to 3. Counter is broken random bag. Write down the probability the counter will be blue. So that was red. That one's blue. So we're going to do 2 to 3 from 5. And if we want the blue, it's 3 out of 5. Okay. So it's about knowing this. The 2 and the 3 is separate numbers. The total is 5. 100 students each choose an activity. Each student chooses bowling, karting or ice skating. So they're only choosing one activity each. Two-way table shows the information about the activity of students. Complete the two-way table. At the moment, this is just a logic problem. You look through and you say, right, how many things have I got where there's only one gap? Well, in this one, I've got a gap here. So to get to the karting, this is going to be my first value. The number of girls, there are 13 boys, I need 7 girls to make it up to 20. Also going across on the ice skating, this is my second one. So 26 and 46, the total is 100. So there must be 54 people who went ice skating in total. Working back up, that says to me that there must have been 20 who went, boys went ice skating. We could have done this one at any time. There are 47 boys, that means there must be 53 girls to make a total of 100. So that could have been done any time. And now we work backwards. We've got 33 people here, and I need 47, so there must be 14 boys in the top. That's my fourth value, and my fifth value is 53 from 41, or 41 from 53 gives me 12. Check coming down, yeah, that works. So the check on that 26 is right. So likelihood is correct. That's all three values. These numbers you don't have to show. I'm just showing them so that when I print it out, it shows what order were they done in. Okay. So just so you know, that just makes sure that I know what order it was done in, and when you see the printed version, you know what order it was done in. One of the boys is chosen at random. What's the probability the boy chose karting? So we're only looking at boys. That means our total we're dividing by is 47. A lot of people make the mistake of it being the 100. First thing is we are only looking at boy. Okay. So the probability a boy goes to karting is 13 out of 47. So let's scroll on down. This is probabilities to be into another probability table. This is called a probability distribution. And what it says is blue is 0.4, red is 0.15. Well, we know the total for all probabilities, and assuming that there must only be blue, green, red, and yellow. So that's all possibilities. And these must make up to 1. So the probability of red plus the probability of green must equal 1 minus 0.4 minus 0.15. The total left is 0.45. Now, here's the big trick that people will fall into. There are 4 times as many green as there are red. So that actually means that the probability green is actually going to be 4/5 of this number. So we've got red to green, and we're going to do it as a ratio. For every 1 red, there are 4 green. That gives me a total of 5. If the total probability for these sections is 0.45, I can calculate how do I convert from 5 into 0.45. So end 0.45 divided by start. And it says I've got to multiply by 0.09. So this value of the red is 0.09, and green 4 times 0.09 is 0.36. Do a check. 9 plus 36 is 45. Yes, we've been counting in hundreds, so it is correct. So I can do green was 0.36, red was 0.09. Okay, So the first thing was working out the probability for both of them, and then the second trick was in this. If you didn't get that combination, you definitely lost 1 mark. You'll get really horrible numbers, which might be a clue as well if you try doing quarters. If you're talking about this being 1 quarter and this being 3 quarters. So remember, 4 times the number of green counters means for every 1 there must be 4 green. It means there are 5 in total for each section. Something similar here with the spinner. 4-sided spinner, it is biased. Well, the outcome is 1, 2, 3, 4. So this shows the probability of the spinner to land on numbers 1 and 3, or 3, 0.2 and 0.1. Now, it's just the same as what we've just done, but this time it says the probabilities are the same. So the total probability is 1, and that is everything has ever happened. So what's left over is probability of a 2 and the probability of a 4 must equal 1 minus 0.3, 0.7. And it says, in this case, it is the same, so each is half. Oh, okay, 4, because they're asking specifically for 4. I will put this back into the table as well, 0.35, 0.35. The probabilities are the same and the total is now 1. Spins the spinner 200 times, work out an estimate for the number of times the spinner will land on 3. Now the probability of a 3 is 0.1, and that's out of 1 total. That's the same as the number of 3s, divided by the number of trials, 200. So we're expecting the spinner to land on the 3s 1/10 of the time. This 1 here is my fractional thing, so we're comparing the probability to the total probability. And now I can do multiply across to give me the 2, and that gives me 0.1 over 1 if you want, multiplied by 200, which is 20. So we'd expect 20. Doesn't mean you'll have it. If I see 20 come up perfectly lots of times, I think someone's fixing the results. Okay, it's not properly random. Question 7. This is an extension task given on one of the lessons. If you haven't done it, you might want to go and look at the notes. The question here is, this actually tells you the how to combine probabilities. And each line is a unique story. So each of these outcomes are independent and are mutually exclusive. The events here don't have to be independent. Something here might affect this one. And the story is we're going along the line and doing AND. So we start over here, and each time we come across a probability, we're ANDing it. AND is a multiplication. So complete the probability tree diagram. Everything at a point must equal 1. So 0.02 means this one must be 0.98. Fine. This one we've been given, so the probability for this to be equal to 1 is 0.95. Now this bit must equal 1 as well. What's the probability of machine B being faulty? Now, it's not always the same in both machines. These numbers can be different. In this case, they've said it doesn't matter, the machine is 0.05. That actually means each machine is actually independent because these two probabilities are the same. And 0.95. That completes the diagram. Each branch point, the total is 1. Probability of at least one bottle is faulty. So which situations? Thus both bottles are faulty. Yes, I want to know what this bit is. One bottle faulty. Not faulty from machine A, but a bottle faulty from B, and not faulty. So what we need to do is calculate the probability of these three events. Now there's two ways, and I'll show you a shortcut in a moment. But the long way is calculate the three probabilities here. Because these are completely independent and can't come in and out, you can't ever do each story on the mutually exclusive side. Because they're mutually exclusive events, you can add going down. So I now need to do the calculation. We've got 0.02 times 0.05. Oops, my calculator's on. And my calculator's got a funny mode on it, so let's see if we can get it into normal calculator mode. Norm. I want norm 1. Okay, let's try again. It might be on norm 2. There we go. 0.001. Come the other way, 0.02 times 0.95. Now a little trick for you is these two probabilities should add up to that one. So 0.02 times 0.95. And that gives me 0.19019. 0.001 plus 0.019 gives me 0.02, and there's another in the end. So that actually worked out. Going the other way, 0.98 times 0.05. 05 times 0.98 gives me a probability of 0.049. So my probability of one or more faulty is the sum of those three probabilities, 0.001 plus 0.019 plus 0.049. Now, because these two were ticked and everything on this bunch was ticked, I actually only need to add in that probability. 0.01 plus 0.019. Sorry, that should be an extra O in front of that one. That gives me my 0.02. That's those two added together. Gives me the 0.02 here, plus this next one. And that gives me 0.069. That's the long way. The quick way is to do the opposite. One or more faulty. The opposite of this is none are faulty. So probably a 1 or more faulty is equal to not of probability none faulty. That's the opposite situation. Not statements are 1 minus probability of none faulty. That none faulty is this probability here, the 0.98 times 0.95. 0.98 times 0.95. So put this in a square bracket. So when you look at the notes later, you'll see that I don't need this number directly. That's 0.931. So 1 minus that number is a 0.069 again. And that's how you can get through in a quick way as well, by reversing the logic. Mark schemes on the end. Questions with stars, be careful about making sure you've disclosed all the information you could. And that's that one done.